Welcome back, boys and girls of North Campus, to another Channel 203 broadcast. Today we will be walking you through the cardinality of sets, what it means to be the subset of a set, and how to get the power sets of a set. We're all familiar with the general idea of what a set is, but for logic, we need a more concise definition. We're going to define a set as an unordered collection of objects who are termed the elements or members of the set. A set is normally denoted by curly brackets, and we have some elements A, B, C. That was a terrible curly bracket, so we're going to erase that and draw a nicer one. We're going to say this is set A. So if we want to say A is within element A is within set A, we draw it like this. This is our notation, and this is the exists symbol. This is read as element A exists within set A. We could say that two sets are equal if they have exactly the same same elements within both sets. So set A and set B are equal if for all of X exists within A, and if and only if X exists within B. And we can see this is only true when X is both in A and in B, and true when X is neither in A and neither in B. Now to Alex with cardinality in weather.
Thanks, Mohammed, and welcome to weather. So, once again, let's suppose that it is raining. But we're going to count all of the raindrops that are falling. And to make it easy, we're just going to say that all the raindrops fall at once and then they stop. So let's assign a number to each of these. So we have raindrop 1, 2, 3, 4, 5, and 6. And if you look at this, this actually resembles a set right now. It's a set of the numbers, or the raindrops, 1 through 6. And we're going to call this set S. And if you look at it, this set has a size, and the size of this is 6, and we denote that with 2 lines. So the size of S is equal to 6. And it's a countable set because if you're a human being, you can count this out. 1, 2, 3, 4, 5, 6. Pretty easy. So now we're going to a bit. Let's take all of the raindrops that fall across the entire world. It's a giant worldwide hurricane tsunami. So let's try to assign each of them a number. The thing is, there's just far too many of them. That's almost like saying there's infinite little raindrops. So this is like an infinite set. An infinite set has an infinite number of terms in it because there's infinite raindrops. So the thing is, it's still a countable set. But you might ask, well, why is this countable? Well, that's because I could count up each one of these raindrops. 1, 2, 3, keep going all the way up to raindrop number 1,000,000, keep going all the way up to raindrop Google. I can count up all of these. It's just that I would never ever stop. So that's the set right here, set R, of the infinite number of raindrops falling on planet Earth. We're going to get kind of abstract. Let's look at real numbers. These are the numbers that exist. We're talking whole numbers, we're talking fractions, we're talking numbers with lots of zeros and crazy decimal points. So if you think about it, it's like taking a raindrop and counting up all the different ways you can divide it up amongst all of them. It's a little abstract. The key thing is that it's uncountable. Well, it still goes to infinity, right? So why is it uncountable? The thing is, you can't put them in a nice list. Let's look. We have 1.0001, 1.0002. The thing is, I've missed an infinite number of numbers in between each of those. There's an infinite number of numbers between 1 and 1.0001. There's an infinite number of numbers between 1.001 and 1.002. So the fact is, you can't count these. They don't revolve around whole numbers, and there's just simply too many of them. Well, that's it for our rainy day look at logic. Now off to Colin with a little logic in education. Colin?
Good morning, viewers. This is Colin Peterson, and today we're talking education, so pay attention. Muhammad introduced you to sets, and Alex walked you through cardinality. Now, I'm going to take you into the field of subsets. Now, suppose you have two sets. We'll call A and B. We call A a subset of B if and only if every element of A is also an element in B. We use this notation. This means that A is a subset of B. In logical terms, it looks like this, and it means for all x, every x that is in A implies that x is also in B. This must be true for A to be a subset of B. Now, consider the following situation. J is the set of students who have at one point attended the University of Michigan. K is the students who at one point attended the Ohio State University. And L is the set of people who are awesome. Now in this case, we can conclude that J is a subset of L because everyone knows that without exception, all students who attend the University of Michigan are awesome. So J is a subset of L. And that's our notation for subsets, if we haven't covered that already. And now, we can also conclude that K is not a subset of L because there is obviously at least one student who has attended the Ohio State University who is not awesome. So our notation for that is very similar, except there's a slash. Now, the same situation can help demonstrate an important method to determine if A is a subset of B. To show that A is a subset of B, you must show that if X belongs to A, then X also belongs to B. For instance, let's take a look at this next example. Alright, the set of me, Muhammad, and Alex looks like this. Now, this is a subset of the students who have attended the University of Michigan because each one of us is also in the set of people who have attended the University of Michigan. So, just to make it very clear, I am in the set of people who have attended U of M, Muhammad is also in that set, and Alex is also in that set. Now, if we wanted to show that A is not a subset of B, you must only find a single X in A that is not in B. Using our previous sets of J, K, and L, we can find a person who at one point attended the Ohio State University who is not awesome. In this case, it's Terrell Pryor. So, suppose X is Terrell Pryor. We can say that we found an X in K, but X is not in L. Therefore, we can conclude that K is not a subset of L. Now, let's move on to a very special set. The set that I want to talk about has no elements. This set is called the empty set, or the null set, and is denoted by a 0. The empty set can also be denoted by a pair of braces. It's worth noting that every set S contains the empty set, as well as itself. That is to say, that the empty set is a subset of S, and S is also a subset of itself. If you want to use subsets to show equality, you need only show that A is a subset of B and B is a subset of A. So that would look like this. This simply means that every element in A is in B and every element in B is in A. so they would have the same exact elements. Well, that's it for subsets. For Channel 203 News, I'm Colin Peterson. Back to you, Mohammed.
Thank you, Colin. Today we're going to take a quick look at the presidential race. Here's a small set of potential presidential candidates. P equals R for Romney, G for Gingrich, and S for Santorum. So we're going to say, what are the possible, which one of these candidates are going to hold their promises? So our first option is that no one holds their promises, which is the null set. Then we have three other options where only one of the candidates hold their promises. So either R, Romney holds his promise, or either only Gingrich, or either only Santorum. So we have three possibilities here. Next, we want to see, our next option is that exactly two of the candidates hold their promises. So either Romney and Gingrich hold their promise, or Romney and Santorum, or Gingrich and Santorum. So this is another three possibilities. And our final, there's only one way for all three of them to hold their promises, which is Romney, Gingrich, and Santorum. So if we add that all up, we get 1 plus 3 plus 3 plus 1 equals 8. That's the number of sets that in which the presidential candidates have held their word. In essence, we've actually looked at the subset of the power set of P. And the power set is any set that is given the set A. The power set of A is the set of all sets of A. And we could go back and prove through what Colin had mentioned that all the sets we have already shown are subsets of P. There's an easier way to calculate this though, where given a set A, we know how many power sets it has using the formula 2 to the n, where n is equal to the cardinality of A. Well, it's really just that simple. And on behalf of us all at Channel 203 News, I'm Mohammed. Stay classy, Ann Arbor.